Swayam Prabha. Digital India. Educated India.
Today we are going to discuss about detection of cracks in shafts. Okay, because predominantly you would have seen if cracks occur, materials and structures fail, but we need to monitor the cracks, and in fact monitor the system so that the cracks can be detected at an early stage, because invariably cracks can occur in any system, be it a shaft, be it a plate. Cracks can occur because of many reasons. Okay. Cracks are sometimes visible if they are on the surface, okay, and if they are invisible, they are inside the body. Okay. Particularly, there are methods. Once there are cracks are occurring in a system, what happens? So, this is a shaft which is rotating. Obviously, its strength is going to weaken, strength is going to decrease, and eventually if this crack goes undetected, the component of the material is going to fail, and then we will have catastrophic consequences because of such a failure. Okay. Imagine a case of a railway axle, okay, where we have these wheels going on these axles, and suppose this cracks occur and then the systems fail, then we are going to have a problem, because there will be derailment, accidents, etc. So, cracks have to be detected at an early stage. Okay. Now, if you will notice here, this crack, a very generic crack, is going to weaken the structure. Its strength is going to decrease. Okay. And once the shafts are rotating, systems are rotating, this becomes still a very complicated issues. Things are rotating, okay, and if imagine if there are weights being carried on the shaft, because they are rotating, these cracks are subjected to varying loads. There will be fatigue loads on the crack. And a material subjected to fatigue loads is going to fail much quickly compared to a static load. Okay. Imagine if I have this as a shaft, and this is rotating, and there is a small crack, and every time this is rotating, this crack is going to open, close, and then eventually because of fatigue loading, it is going to fail much quickly. Okay. This is something which we need not, we should not do. This is one type of cracks, and in this class we are going to focus on such cracks on shafts which are visible from the outside and how we can reduce them. But cracks do occur in structures, like I was telling you, inside the structure, outside the structure. If it is inside the structures, it is very difficult to visually see it. So, people do what is known as the ultrasonic inspection, and we are going to study about this later on. Ultrasonic inspection, or what is known as the NDT type of tests. Okay. But one thing you will notice here, if a crack has occurred, the machine or the local area around the shaft is going to be not that stiff. It is going to have stiffness is going to reduce. Stiffness is going to reduce. Reduce is a pretty strong word. I would say stiffness is going to change if a crack has occurred in a system. Okay. And you will recall the natural frequency of any system is root over k by m. So, if there is a change in the stiffness, obviously there is a change in the natural frequency. So, with this, you will see there are methods by doing the eigenvalue analysis of a system. We can find out the change in natural frequency and then say maybe a crack has occurred. The system's transfer function is going to change. If you all recall, the mobility of a system is defined by force by velocity, isn't it? Okay. And then we have the impedance. Impedance is inverse of mobility, isn't it? Okay. So, by giving an excitation to the system, some force, by measuring some velocity, I can find out the system's impedance. Okay. So, system's impedance, in fact, this is impedance. Yeah, impedance is force by velocity and impedance is inverse of mobility. So, by giving an excitation to a system, I will measure its response. If a crack has occurred, okay, this mobility is going to change. That is also another way of detecting a crack of a system has undergone or not. Okay. Before we go into the discussions on the methods to find out cracks, let me tell you what are the two types of cracks which can occur in a shaft. Okay. So, in this class, as I was telling you, we are going to focus only on shafts which have cracks, and cracks which occur inside structures will be dealt when we discuss about ultrasonics. So, a load on a shaft could be because of bending loads. Shafts are supported on bearings. These are bearings. Okay. There could be a crack and there could be some bending load because of a weight. Okay. And then we are going to have this kind of a crack, which is usually transverse almost in this line. These are transverse crack. Okay. And if I exaggerate it in the drawing, so each type, the crack is the shaft is rotating. At once it comes to the bottom, because of the loads, it is going to close. Suppose there is a load here, strong load here. It is going to open and close. Once it goes to the top, this crack is going to close, and again it comes down. It will once it comes down, it will close. It goes up, it will open. So, this opening and closing of cracks occur in a rotating shaft, and this is known as the crack breathing. Now, to our naked eyes, at times this will be not visible at all. Okay. And another parameter by which the cracks are defined is actually, if this is the diameter of the shaft as d and the crack depth is a, is a non-dimensionalized parameter a by d, crack depth to the diameter. And usually, of course, if the a by d is 0.5, it is almost till the diameter. I mean, no system would go till even 0.5, because the structure would have become so weak, it would have failed. Usually 0.1, about 10% of the d, a is equal to, is the limit. I mean, beyond which we cannot have any structure sustain loads beyond crack depth of 10% more than the shaft diameter. Okay. So, we have to keep a track on this is the parameter by which this crack is defined, and this is usually negligible. It's like an hairline. No, if you are talking about a crack of a shaft of about 12 mm diameter, even this dimension could be about 0.5 mm. Okay. Very thin hairline crack. Okay. In our laboratory, I will show you. We have done experiments wherein we use a hacksaw to cut a slot and make a crack also, and that's a massive crack. I mean, having a hacksaw cutting a slot on a shaft. Okay. But usually these cracks are hairline cracks. Okay. This is a type of crack, and which is known as the transverse crack because of the flexural loading on the shaft. Okay. Another important thing happens actually, as you know, the shafts usually carry torsional loads. They transmit power, so they carry a lot of torque. And usually, because of the torque, the maximum shear stress occurs in the 45-degree lines. Okay, if you are transmitting torque, usually the cracks are at this 45-degree axis and somewhere here. Okay. And these are the slant cracks. And if you see cracks oriented on a shaft in these lines, you can know these cracks are because of the torsional loading on the shaft and not because of the flexural loading. Flexural loading, as I just told you, they will be transverse in nature. So, essentially in shafts, either a transverse crack occurs, a slant crack occurs, or a combination of them, both of them occur because of the type of loading which is there on the shaft, which is usually a flexural loading because of the bending forces, or the torsional loading because of the torsional moment which the shafts are carrying. And so, what are the symptoms or signs by which we can detect whether a crack has occurred through vibration monitoring? Number one is the stiffness will change. Okay. So, we can monitor the eigenvalues or the natural frequency. Number two, the mobility inverse of the impedance, mobility will change. So, we have to do through impedance measurements. Of course, once we are discussing through vibration monitoring, there are techniques beyond vibration monitoring by which cracks are detected, and these are usually stationary cracks on structures. One is through the NDT techniques of dye penetrant test, particularly to find out hairline cracks on castings. Particularly, I will just give an example. So, for example, we cast an engine cylinder block. Okay, there are. So, this is some view section of a cylinder block. Okay. And a crack has occurred, a very thin hairline crack. Okay. Now, if you see a cylinder block, there are many things which happen. There are in a cylinder block, there are a lot of water passages which are made in the casting itself, so that the cooling water goes all around the cylinder block. Okay. Now, they are under pressure. So, if there is a crack, what is going to happen? This water is going to ooze out. Okay. So, how do you detect such kind of cracks? So, that is why they do what is known as a dye penetrant test. After the cracks are after the castings are done, they smear it with a dye, okay, and then rub it off. And if the crack is there, this dye, after you have smeared the surface the dye, and this dye will make a mark, ooze out and clearly show that crack has occurred, just looking at the dye. And this dye could be not visible in the naked eye, it could have a fluorescent lamp where the dye is going to glow, and then you can clearly see that a crack has occurred. That is one way, which we will discuss later on in the ultrasonic in the NDT section. And another crack detection technique, which they do for shafts which are rotating, particularly imagine in railway bogies or wagons, rolling mills, paper mills, cement plants. Here we have a axle of the train which is rotating. If the crack is inside, it will have consequence that the structure is going to weaken, it will fail. Rolling mills, a lot of rolls are there which run continuously. If a roll breaks, the steel plant, the cold rolling mill or the hot rolling mill cannot produce. Paper mills, there are about 100 200 mills rolling rolls. The rolls crack, the paper mill is going to get shut down. Cement mill, the rotary kiln, okay, big shell about 2-3 meters in diameter, which rotates. If there is a crack, okay, eventually the system is going to weaken and fail. So, these are actually tested by an NDT technique of ultrasonics. Okay, we will discuss about the dye penetrant and the ultrasonics in the later class, but again in this class I wanted to focus on the dynamics of cracks in a shaft and how do we monitor it. So, we know that we can measure the mechanical impedance of such a system, we can measure the natural frequencies of a system, because if cracks occur, the stiffness is going to change, and so the natural frequency is going to change, and then let us see how we can do that. Okay. This is a setup here which we have in the laboratory, and if you can see here, we have a crack, and if you will see, there are two discs of aluminum, two flanges basically, and these flanges are held together by 4 bolts, and eventually if you will see here, this is actually a crack shaft. Okay. Shaft is totally cracked, and to simulate cracks, what you do is tighten these 4 bolts, okay, loosen maybe the top 2 or any 2 or any one, so that at one end of the crack, maybe if I draw it here, if you see here, we have put 2 flanges. They are actually 2 crack shafts already, and then if you bring them together and then put bolts, okay, we join them kind of, and then if you loosen this and tighten this cracks maybe, this shafts maybe could be like this. Okay. So, to stimulate crack, we do this in the laboratory. Okay. And what we do here is, again, when we have a crack shaft, we always measure at the bearing locations. As I told you beforehand, in condition monitoring, usually when you monitor rotating machines, this is the only good place we have to keep the transducers, and here also we have to keep the transducers on these 2 bearing locations. And this black disc here is actually a loader. It's a heavy weight which is rotating on along the sides these cracks. So, that this is responsible for giving that load, bending load which is coming down, and which will be responsible for opening and closing of the crack and create this breathing mode. Okay. So, we have you got the vibration measurements from this system, and I will show it to you later on. And then we will another setup which we do is to find out the mechanical impedance. Like I told you, the techniques for detecting shaft cracks are mechanical impedance and then the eigenvalue analysis. Okay. This is an experiment which we did in the laboratory, okay, and this is a shaft wherein, and if you will see, this is about a 12 mm shaft, and where we cut a sawtooth crack onto the shaft, okay, by using a hacksaw. Okay. Now, because of this, we rotated it at a particular speed, and then we tried to see what is the change in the mobility. Okay. Actually, these two graphs summarize the results. Let me explain you what we did here. Okay. What we did essentially is we measured the mobility. Okay. Now, to do that, what we did is we have this system wherein you see this shaft where is a heavy disc, this particular heavy disc here, okay, and then where we introduced a crack very close to the disc. Okay. So, this disc is responsible for opening and closing the shaft, and we try to measure the impedance of the system at any one bearing locations. So, what we had is an exciter. You see this black one here is actually an exciter, okay, and this exciter we are giving a force signal. So, this exciter is exciting the structure, and here what we have is an impedance head. Impedance head is a transducer I told you, which has a force gauge and a accelerometer together. So, that I will measure the acceleration of this system and measure the force which is being applied. This acceleration will be single integrated to get the velocity. So, I know the velocity, I know the force to this system, and then thus I know the mobility. Okay. So, mobility of the system is known for uncracked system when we did with two measurements, with a good system wherein the shaft had no crack, and next we replace that shaft with a shaft which had crack. So, we have these two ratios, the response to M cracked with M original, mobility with cracked system to mobility with the uncracked system, these two ratios. Okay. And then you will see here, this is at this x axis is the crack depth alpha, which I told as A by D. We have gone as high as 0.4, pretty high. Okay, A by D is 0.4, and we have run the system at two different frequencies. One was 22.75 hertz and one is at 40 hertz. Okay. And you will see how with crack depth suddenly this mobility changes. Okay. And this is a good indication that by monitoring the mobility of a system, I can tell that the system has undergone a crack. Okay. Just by monitoring vibration, I would not be able to tell whether a shaft's crack has occurred. Okay. And this is actually published in one of our journal papers. Okay. So, to summarize, this for different various crack depths and different mobility is very sensitive at and these are at the rotational speeds 22.75, 40 hertz, 22.75 at 120 hertz, and so on. At different speeds we have seen the mobility. So, in a system, if we want to say, for example, let us talk about a gas turbine. Okay. So, if you want to place a system in a gas turbine to monitor whether cracks have occurred or not, you can do this. Gas turbine has long rotors with sets of compressor blades, low pass, low pressure stage, high pressure stage, combustion, and then the turbine, etc. All these are sets of vanes. Compressor, turbine, etc. So, what we have to do is do through a modal testing through experimental modal analysis. Well, what is experimental modal analysis? Basically, we find out the transfer function of a system response to the excitation. Okay, in our case, mobility is nothing but velocity by force, and impedance is force by velocity. So, to a unknown system where we have to do crack monitoring, all we have to do is give a certain known force at the frequency of operation. Suppose a gas turbine rotates predominantly at say maybe 24,000 RPM to maybe 30,000 RPM. Okay, and this will correspond to 24,000 by 60, 400 to 500 hertz. Okay. So, from a range of 400 to 500 hertz or few of its multiple, you excite this system through a force. How do you excite the system? Through an exciter. Usually, because it is a large gas turbine, we can use heavy electrodynamic exciters. I give a known force F from the frequency maybe 400 to 2000 hertz, and at the same time at the bearing locations obviously, but in the turbines, because they are supported with many bearings. Okay. At any of the bearing locations, you can measure the force, and then with the suitable transducer you can mount an accelerometer, etc., measure the velocity, measure the force, and plot a mobility curve V by F as a function of frequency. Okay. And then now all you have to do is continuously keep on monitoring V and F. By continuously, I mean you need not do the force, give the force excitation every time, but momentarily every day once you measure V by F. Every day once you measure V by F. Suddenly you will see this V by F, if we do the ratio of the, so this is my original and which I say as m naught, okay. And then you will have m nu. M nu is V nu by F nu. So, you will plot m naught by as a function of frequency, and you will see that with a crack occurring suddenly they should have shot up. Okay. Like you go back to the slide here, I am plotting m nu to m naught as a function of crack depth, but at particular frequency I can monitor them. Okay, and these frequencies are the operating speeds, and I will see that with particular crack depth it is increasing. Okay. If the crack depth has increased, this value is going to increase, okay, because you see this is crack depth. If crack has increased, this is going to increase. Okay. So, at a particular frequency I can decide on the frequencies. Frequencies usually will be the operating frequencies. Operating frequencies, and this is out of our research which we did about 10 years ago, okay, and just measuring the mechanical mobility of system to monitor cracks occurring in a system. You can get a reference to this paper at my website. This has come out in JASA in year 2002, okay. Volume 112, number 6, pages to 2825 to 2830. The details about this technique are given in that paper of ours, okay, wherein just by monitoring the mobility of a system, we can tell whether a crack has occurred in a system or not. Okay. Now, let us, so in a nutshell, to monitor the occurrence of cracks in large systems, you have to measure the mobility of such a system periodically, and if the mobility value increases, you will get an indication that the crack has developed or crack is growing. And once happens, crack also takes times to grow, and that is what is saving us. If the cracks occur suddenly without no reasons and they did not grow and they just fail, it would be disastrous. So, crack takes time to grow, and this helps us in the prognostics. Okay, you have the the famous Paris equation for the crack growth rate. That depends on the material property, the crack dimensions, etc. So, it takes time to grow, and eventually crack will grow to such an extent that material would have become weak and it would fail. But through a mobility measurement, initially when the crack has occurred and it has just grown to few A's, 0.5, where A I define as the crack depth by D, the crack has increased, we will see that the mobility value suddenly shoots up. So, mobility is sensitive to crack other than just monitoring the velocity of vibration. By velocity of vibration, it would be very difficult for us to monitor whether the crack has occurred, but by doing the mobility measurements, we can surely say the crack has occurred. This is what actually happens. Is another view, the better drawing of that is, this is what I meant by this crack occurring at a distance. Crack can have a maximum distance of L at a location X from one of the bearings. So, there is a rotor here, the shaft of diameter D, and A is the crack depth which you define as. Okay. And because of these, there will be forces coming in the bearings, the stiffnesses are going to change, displacements are going to happen, and so on. Okay. And when the crack shaft rotates, this is how the stiffness varies. This is what is the breathing model for the transverse crack. Okay. In a complete rotation, this is how the shaft undergoes. Okay. The stiffness changes, the flexibility changes, because the cracks are opening, closing, opening, closing. At any location, the flexibility which I measure at the bearing locations are going to change. Okay. The stiffness is going to vary. Now, let us see what happens in the case of the breathing behavior for a slant crack. Here, I am subjected them to a torsional loading, okay, and the cracks have occurred in the 45-degree axis. So, cracks will once open and once close. This is also the breathing behavior of a crack, but it is slant. But then the question would be, how do I distinguish between whether a crack has occurred because of a torsional load or because of a bending load? Because once you have to do the diagnostics, okay, you will see eventually a crack has occurred in the 45-degree axis. Okay. But if you are measuring the vibrations, you would not know perhaps whether it is a breathing mode or because of a slant crack or a transverse crack. And how do you, because I need to know the cause of the crack. Was it a transverse load which created the crack? Was it a torsional load? Or another fundamental question which you will be wondering is, okay, a designer would have taken care of the loads. So, why crack is occurring? Okay. To answer that question, there are many ways. So, these materials which are used to make the case of a shaft. So, for example, let me take the case of a pulley. By pulley, I mean a pulley of a conveyor system. It is not the conventional pulley which we use for power transmission in our maybe small motors or pumps, but I am talking about conveyors where and these are actually supported on bearings, and this length could be about 2 meters. Just give a feel of the dimensions, and this diameter could be about 0.5 meter. Okay. And this thickness of this, it is a hollow drum, okay. And then there are some end plates here onto which we put a shaft, okay. And this thickness is about 20 mm. Okay. Now, the shaft is solid, solid shaft onto which we have the end plates. This is the shell. Usually on this shell they usually put a rubber material to protect the shell. Okay. This is known as the lagging. Rubber material, and in a conveyor, okay, there could be series of such pulleys, okay, and there will be this conveyor which is going on these belts, okay, and this could be a big ship here, okay, carrying maybe coal, okay, and then there is a crane here at the port, okay, which will scoop and then drop it at a bin, and then this is getting transferred, and this comes to the place where there will be railway wagons, okay, carrying the coal and out, and this could be as long as maybe 1 kilometer. Okay. And each of these, these are there maybe 5 meters apart or 2 meters, 5 meters apart. We have put this conveyor pulleys, and they could be carrying coal at the rate of maybe 5,000 tons an hour. Okay. This is the typical scenario of if you go to any port, okay, either the loading circuit or the unloading circuit. Either in our country, in all of the ports, we do unloading on the loading of the iron ore. We send out the good iron ore and get the good coals from outside, because we have coal, not good coals in our country, or we get the coals in and the iron ore goes out in the conveyor systems. And in such a system, if a crack occurs in a pulley of the conveyor is not going to work. Okay. Now, question is, a designer would have done a good design to ensure that the cracks or this conveyor system does not fail, but there has been instances. I have seen some of the pulleys. The material of the pulley, okay, is supposed to be isotropic, steel of a particular grade. Usually it is low carbon steel, okay, with a particular, these pulleys are made out of plates. Okay. these plates are produced by hot rolling. Okay. And then they are welded at one location. They are welded at one location. And imagine welding a 20 mm plate. Okay. There will be a lot of heat concentration at one zone around the weld, and that is known as the HSZ, heat affected zone. So, usually after welding you have to do good amount of post weld heat treatment. Post weld heat treatment. Otherwise, what happens, if you look at the microstructure of such systems, such plates around this, you will see that the grain sizes are not uniform, and there could be banding in it. And this could be ferrites, and this could be pearlites, and this banding gives rise to alternate hard and soft areas around the weld. Okay. For a designer, when I design it, when I take a value of stress, I assume that the stress is uniform everywhere, hardness is uniform everywhere, that is fine. But when I manufacture it, when I have done on welding, my heat treatment was not proper. I have artificially created high zones of soft material, high zones of hard material, and you are rotating a soft and a hard material together. Okay, one zone is soft, one zone is hard, and this is how, because of one inherent defect, this crack is going to originate. And then if one crack goes unnoticed, it is weakening the structure, few more cracks will come up, and then once cracks start to propagate with time, because you are rotating it, cracks will propagate and eventually the system will fail, and this is what actually happens. And that is why you will see all those bridges which see in our country, Howrah Bridge, the new bridge, why do they never weld those structures? Do you know why they do not weld? Because of these problems. That is why they rivet, they make a hole and rivet and bolt, because heat treatment cannot be done at such a larger scale in situ in a large place where you are going to weld things. Okay. So, post weld heat treatment is very, very essential to prevent failures in mechanical systems. Many mechanical structures systems have failed because of crack, because of fatigue, only because the post weld heat treatment was not done correctly to ensure that I have uniform grain size. So, otherwise the material is going to have hard zones, soft zones. The temperature time cooling curve after welding is very, very important. If you have studied iron carbon diagram, you see how the carbon if you quickly cool it, you will have a hard material, there will be a lot of martensite formation. We have to slowly cool it, there have to be a lot of pearlite formation. So, heat treatment becomes essential, but as a maintenance engineer we need not worry about it. We assume that the guys who have designed it, who have manufactured it, would have taken care of these. But when we go to site, a system has failed, they will all point to the bearing, because that is why we have where we have put the transducer. They will say because the bearing has failed, the whole system has failed. No, that is not true, because the person who had manufactured it did not do a good weld job, perhaps did not do a good post weld heat treatment after the welding. So, such variations in the microstructure occurred, such hard variations in hardness occurred, and thus the crack initiated. Okay, this is one case study you all should remember in particular. And usually I should tell you, usually when you are doing an welding, actually when you weld, you have to go to the melting point temperature. Usually for steel, if a plate is 20 mm thick, immediately after welding, you have to hold at that weld temperature that material which have been fused for about 1 hour. That means you should not cool it suddenly. If you quench it in a cold bath, there will be brittle surface on the top, it will harden and then it will crack. Okay. So, we have to always hold it. Many times the fabricators at site do not do this, because to hold it at the temperature you have to insulate it. Usually an asbestos cloth is put over the weld, and even before you weld it, suddenly you cannot bring for a room material from a room temperature and suddenly start to heat it. They are slowly heated up to bring to a temperature, okay, and then the welding is done, held for 1 hour at that temperature if it is 20 mm thick, and then slowly it is cooled, and that is usually done by covering the weld with an asbestos cloth. And if you do these things, you can avoid cracks in systems and shafts. Okay. Another reason, of course, the cracks occur because of casting defects, blowholes in castings which go undetected, poor casting, and then of course, these blowholes etc. can be checked by ultrasonic testing. Okay. Now, this is another thing. In the last few slides before this, we had shown you about mobility. Here, we will show you about the change in eigenfrequencies, okay, or the natural frequencies once the crack occurs. This is again the normalized eigenfrequency, the first 3 eigenfrequencies. With crack depth increasing, you will see at some particular frequencies they are very, very sensitive to the change in the eigenfrequencies. So, eigenfrequencies, mobility are true indicators that a cracking has occurred. If you just monitor one eigen frequency, you may not be able to see, you have to normalize them with respect to the original natural frequency, how much is the variation. With respect to the original mobility, how much is the variation. Just by doing an absolute mobility measurement or an eigenvalue measurement, you will not be able to know what the change has occurred because of cracking. But if you take the ratios, this clearly show that this kind of changes do occur. Okay. Now, a lot of signal processing techniques have been used to detect crack also. Particularly, though, in this class we are not going to discuss about the details of non-stationary signals. I will just tell you briefly. Particularly, when you start up a shafting system, or which is known as a coast up or coast down. Okay. And if you do something what is known as an wavelet analysis, and if I have a shaft some velocity presence of subharmonic lobes indicates cracks. and this can only be done when we excuse me, when we coast up or coast down a system. By coasting up, I mean changing the speed, ramping up the speed, okay, from 0 to some value. When you are ramping up, because the signals are not at constant speed, this is a non-stationary signal, then we can see this kind of lobes happening once you do an wavelet analysis. Though in this course we are not going to discuss about wavelet analysis. So, through advanced signal processing technique, we can also detect cracks. Okay. Earlier, people were never monitoring cracks through such vibration monitoring. They only did an NDT test either through ultrasonics or dye penetrant to locate cracks. But nowadays, with the improvement and the understanding of the science, and then these algorithms have come up, people can find out the occurrence of such cracks in such systems. Okay. Now, to do the impedance analysis of the cracks in the laboratory, these are some of the data which we used. The length of the shaft was about 50 centimeter, diameter was 2 centimeter, and the density, etc. And then the first eigenvalue was 24.27 hertz. Rotor was rotating at 9.55 hertz. With this kind of simulation, we did the analysis, and this last table here gives an indication of how do you comparison of the transverse crack with slant crack. So, when there is a breathing, opening and closing of crack, cracks breathe with a frequency equal to rotation of shaft speed in the transverse crack, and in the case of a slant crack excuse me, they breathe with a frequency equal to the torsional frequency. Here in the transverse crack, the eigenvalues reduce significantly compared to that in the case of the slant crack. In the steady state response, the FFT shows the characteristics 1x, 2x, 3x, but in the slant crack they show the subharmonic and superharmonic of the rotational speed. By sub means less than the rotational speed, super means more than the rotational speed. In transient analysis, we can use the wavelets to detect transient crack, like I told you, and then in the case of the response to impulse, when I give an impulse force, the normalized mechanical impedance is highly sensitive to crack depth in the case of the transverse shaft, and in the case of the slant crack, it is relatively less. So, to summarize what we discussed today, cracks can occur in structures, cracks can occur in rotating shafts. To monitor the cracks in rotating systems, we can use the method of eigenvalue analysis or the mobility analysis to find out whether cracks have occurred. To find out cracks in structure, we can do NDT testing of structures by ultrasonics or dye penetrant. Okay. And this cracks in rotating shafts could be either transverse or slant, and the transverse cracks are created because of the flexural or the bending loads, and the slant cracks are created because of the torsional loads. And you have seen the relative sensitivity of the one crack to the other towards mobility, towards eigenvalues, and which could be used as indicators for detecting cracks in rotating shafts. And of course, cracks do take time to grow, and that is the breathing room we have till we take remedial measurements. And cracks, why they occur? Because of defects in casting, defects in welding, post weld heel treatment was not appropriate, the raw material during rolling was not appropriate, hot rolling was not done properly, and so on. Okay. Thank you.